part 3 for this chapter 27, we're going to look at non-coding DNA. Well, you do know that we talk about exon and introns. Well, this is actually non-coding promoter sequences, which are regulatory region of DNA that determine which of its genes are turned on. Now, this is very important because when you look at here, the data, where we have information that suggests that only about 1.5, sometimes they say 2% of all the DNA in the human genome actually codes for protein. The rest are going to be those introns. So if you look at this here, you have coding segment, the exon, and they are alternated with non-coded segments, the introns. Now, when the exon, the signal, and the noise, the intro ratio is very low, we say 1.5%, 2% only of the human genome DNA code for anything. That means that here it is going to be very challenging to completely identify all the coding sequences that are present. So initially we thought, okay, well, finding the gene on the DNA is going to be a very hard task, taking 4 years, went much faster, but now we realized that we have information that will just select specific exon to be used for making proteins. Another thing I want to emphasize on is mutation and then polymorphism. So mutation is anytime there is an error in the base sequence that is carried during the replication of the DNA. That's what we call mutation. Well, mutation can be very bad, but mutation can also be helpful, and that's part of evolution. So any mutation actually refers to variation in a DNA sequence that you find in very small number of individuals of any species. So some of those mutations can be spontaneous and random events. Others are induced by exposure to what we call a mutagen. This is any agent that can generate or cause a mutation. Example below: viruses, yes, viruses, kind of scary. Chemicals, cigarette smoking, nicotine, we do know it's one of those. Ionizing radiation can be mutagenic. And on that table, they just give you some example of some of the commonly hereditary diseases, their cause, their prevalence in the population, 1 in 40,000, 1 in 3,000. This is talking about PKU, albinism, Tay-Sachs disease, cystic fibrosis, or sickle cell anemia. Other point important here in that lecture is talking about polymorphism. Those are variations in the nucleotide sequence of DNA that are just common with a given population, making every person very unique. So it's just differences in the sequence of DNA between individuals, and this depends on their geography, where they live, ethnic differences, and this is what really makes the biodiversity that exists on Earth. Most of those polymorphisms are seen that either have an advantage or an effect that will be not good, so deleterious. Some have been shown to give rise to some of the diseases that we can find. And just showing you right here, single nucleotide polymorphism and some disease, if you just replace one nucleotide by another in a specific area of the DNA, this is what we call a single nucleotide polymorphism. Here you see that T, thymine, is replaced with C, cytosine. So disease associated with that, where we call those SNPs. They range from negligible to normal variation, and the one we can find such as in eye color, hair color, but also genetic diseases. SNPs are the most common source of variation between individuals in all humans that we can find on Earth. So looking at this, well, in addition to producing a change in the identity of amino acid, a SNP might specify a same amino acid. So if you change GUU to GUC, both of those code for valine, so it would have no effect. But sometimes if you have one change, you may terminate the synthesis of protein by just introducing a stop codon.